Hello friends, and welcome to another sleepy science journey. Tonight we drift through the question hiding in every glow. What is light actually doing when nothing seems there to carry it? Why can a beam turn, split, encode a message, yet never outrun its own limit? If color is a rhythm, who keeps the tempo? Hold a slow breath and follow the clues, mirrors, prisms, shadows, warmth, clicking quietly into place. When curiosity feels steady, let the first clear idea arrive. Light is the quiet visitor that needs no road to arrive. It crosses emptiness without a vehicle or a carrier, yet it delivers energy, pattern, and information wherever it goes. In physics, it is an electromagnetic wave, self-propelled by changing electric and magnetic fields that sustain one another with perfect balance. In quanta, it arrives as photons, discrete packets without rest mass, bearing momentum that can push on matter with a pressure so slight it becomes powerful only across long distances and long hours. Our eyes tune to a narrow slice of this spectrum. That slice is not special to the universe. It is special to us, shaped by our star and soil and the chemistry of vision. Beyond what we see, the spectrum spreads in both directions. Longer waves carry heat and communication. Shorter waves probe molecules, reveal stars' atmospheres, and map high-energy events. Light does not require air or water to move. It flows through vacuum because the fields themselves are the traveler, not the medium. When light meets matter, it can be reflected, bent, absorbed, or re-emitted. The outcome depends on structure and scale. Smooth surfaces return orderly reflections. Rough surfaces scatter direction. Transparent crystals can split a single beam into two, each following a slightly different path inside the lattice. Color is frequency made visible. The sensation you call red or blue is your biology, reading the rate at which the fields oscillate. Yet color, in the world, depends on context, on the lamp that shines, the pigments that absorb, the surface that scatters, and the brain that reconciles it all into a steady scene. Under one lamp, a shirt looks warm. Under another, it cools. Cameras measure numbers, perception, stitches, meaning. Light is measurement, but it is also experience. On Earth, scattering in the atmosphere paints the day. Small particles and gas molecules nudge shorter wavelengths more strongly, filling the dome above with a pale tint and letting longer wavelengths travel more directly near the horizon when the sun slants low. In water, different rules apply. Red fades early with depth, while blue persists, so sea life adapts and signals within that palette. In technology, we route light through hair-thin glass across oceans. The signal survives because the glass keeps the beam inside by total internal reflection, turning a strand into a corridor for conversation. You can think of light as a clock because it marks intervals with regularity, and as a ruler because its wavelengths and travel times define distance. Telescopes read faint spectra to learn which atoms sit in distant atmospheres, which stars spin, and which clouds form new suns. Instruments on Earth calibrate their lengths against known wavelengths, tying human measures to universal rhythm. Light is messenger and metric at once. Before we drift deeper, pause with me for one soft heartbeat of calm. If you enjoy soft science at night, please like, share this moment, and subscribe to catch the next wander. Light moves because changing electric and magnetic fields sustain each other in flight. A variation in the electric field produces a magnetic response. The magnetic change restores the electric one in turn. This reciprocity creates a wave that requires no substance to carry it across space. The mathematics that binds them is compact and consistent. From those relations, a definite travel speed appears. set by constants measured in the lab and echoed throughout the cosmos. That speed is not borrowed from air, water, or glass. It belongs to the fields themselves, steady as a pulse that never tires. All forms of this radiation share one nature and differ only by frequency and wavelength. Long waves swing slowly, with crest spacings stretched wide. Short waves tremble quickly, with peaks packed tight. When the wave meets matter, electrons respond according to their own natural timescales. If the oscillation matches a resonance, energy couples strongly and is absorbed or delayed. If it misses, the material may respond weakly and allow passage. This is why one pane permits a broad band to cross, while another blocks a slice completely. Materials are not passive windows or walls. They are tuned instruments with notes they favor and notes they refuse. Polarization describes the direction in which the electric field points as the wave advances. In one case, it rocks back and forth along a line. In another, it rotates at a constant rate, like a hand on a clock face. Devices that admit only one orientation reduce glare from reflective surfaces and recover contrast lost to scattered light. The sky scatters this orientation unevenly, producing patterns that some creatures can read for navigation when the source is hidden. Orientation carries information quietly, a second channel layered upon brightness and color. At a boundary, the wave divides its fate between reflection and transmission. The angles follow simple ray rules, weighted by how each medium delays the phase of the fields. That delay is summarized by an index that compares the pace inside a material with the pace in emptiness. The index is not identical for all colors. Shorter wavelengths often slow a bit more than longer ones, so a fan of hues spreads from a prism or a lens, brings different colors to slightly different planes. Optical designers counter those spreads by pairing elements whose dispersions compensate, bringing a broad range of wavelengths to a shared focus. Clarity emerges from cancellation artfully arranged. Patterned boundaries deepen the story. A regular array of lines or slits turns incoming waves into an angular spectrum, sending each color toward a particular direction. The spacing of that pattern is the rulebook. Small separations yield wide spreads. Large separations yield tight ones. Thin films act as layered paths, where reflections from the top and bottom surfaces meet again. If their path difference aligns just right, one color brightens while its neighbors dim. The visible world displays these controls casually on a transparent wing, on a drop of oil, on the sheen of a compact disc, each a calibration card composed by structure rather than paint. Pulses are many frequencies traveling together. Their envelope can slow inside matter because different components advance at slightly different rates. Near a resonance, this difference becomes dramatic, and the shape creeps while the rapid oscillations within still race. Under special laboratory conditions, that envelope can be stored in an ensemble of atoms and later released with its pattern intact. The energy sits in the matter, while the map of the light waits in atomic states. It is not a frozen photon. It is a borrowed message returned on command. Waves carry momentum in their fields, and the direction of travel marks the flow of energy. When a portion reflects from a surface, the change in direction tells you that push has been delivered. Over long periods and broad areas, the effect adds up. Mirrors on spacecraft tilt subtly to harvest this pressure, adjusting orientation with no propellant consumed. In the dust that rings young stars, the same pressure sorts particles by size, guiding growth and clearing lanes where future planets may circle. The language of waves also explains why images blur when openings are small. Every aperture spreads the beam by a fixed relationship with wavelength and diameter. Make the opening wider or choose shorter wavelengths, and the central spot tightens. Instruments at the limits of resolution stretch both strategies. Telescopes enlarge their mirrors. Microscopes venture into ranges where smaller wavelengths reveal smaller structures. When physics denies further narrowing, computation helps by gathering views from shifted positions, or by measuring phase explicitly, then reconstructing structure consistent with those measurements. The wave never breaks its rules. We learn to work within them. Orientation, delay, and boundary behavior also govern reflection beneath a surface. When a wave tries to pass from a slower medium to a faster one at a steep angle, it may find no pathway that meets the Snell law angle condition. Beyond that critical angle, all of it reflects, trapped by the mathematics that would otherwise place its transmitted direction outside the mirror's reach. Cables of glass use this confinement to keep signals aligned for thousands of kilometers. Small imperfections accumulate as loss, but careful purity and gentle curves preserve most of what is placed inside. Communication becomes a guided wave, threaded through a flexible corridor. The spectrum extends beyond what we see, yet the same rules hold. Longer wavelengths thread through clouds and foliage differently than shorter ones. Shorter wavelengths interact strongly with small particles and fine structures, producing images and measurements that reveal composition and temperature. Instruments arrange filters and sensors to receive only chosen bands, translating field behavior into pictures and numbers that can be compared across years and worlds. Calibration ties those numbers to references that do not drift, anchoring observation to constants rather than memories. If a single image would help the mind settle, picture a taut line woven from two strands that take turns leading, each pulling the other forward without friction. That is enough. The reassurance is not poetic, it is practical. The same statements that let an antenna radiate efficiently also let petals shine with specific sheen and allow long cables to carry a whisper without losing its shape. A single grammar serves ships, bees, labs, and stars. The wave proceeds because reciprocity never fails it, because the fields sustain each other with exact fairness, and because space itself offers no resistance to their passage. As the tide shifts, consider how often this hidden order steadies daily life. A screen's clarity in daylight depends on polarization control. A camera's crispness under evening lamps depends on dispersion management. A conversation crossing an ocean depends on confinement by total internal reflection. None of these devices negotiate with the wave. They arrange themselves so the wave's preferences work in their favor. When the day grows quiet, that knowledge can feel like company. Patterns continue, even when eyes close, because the rules do not sleep. When light trades energy with matter, it arrives in discrete amounts tied to frequency. One packet is enough to trigger a change if the binding energies allow it. If the packet is too soft, no amount of brightness helps. If the packet's energy suffices, the exchange occurs as a step rather than a smear, and the effect can be timed and counted. This stepwise behavior shows up wherever electrons leave a surface after illumination, or a molecule flips from one state to another upon receiving exactly the right color. The relation between color and energy is a fixed proportionality, simple to state and profound in reach. These packets carry no rest mass, yet they deliver momentum along their path. When they bounce from a mirror, the reversal doubles the push they give. The force on a tiny surface is feeble in an instant, but relentless over hours and years. Dust spirals outward from stars because of this persistent nudge. Tail orientations of icy travelers through the outer system follow that pressure faithfully. In quiet rooms on Earth, light focuses tightly enough to hold transparent beads near a point where intensity peaks. The gradient pulls the bead back toward balance whenever it wanders, making a trap that is springy but gentle. With such a trap, forces from molecular motors, elastic filaments, and flowing fluids can be measured without tearing or bruising the specimen. Send single packets, well separated in time, toward an arrangement with two narrow paths, and their landings still form an interference map when many arrivals have been collected. The pattern emerges because each packet's probability spreads across both ways until the instant of detection. Place a probe that distinguishes the paths, and the pattern fades to a simple sum. The result does not contradict wave descriptions. It clarifies how questions shape outcomes. Information about which route removes the phase relation required for fringes. Information withheld preserves it. Choice of measurement is part of the physical situation, not a story added after the fact. Pairs of packets can be born with linked properties that defy classical limits on correlation. Create them by converting one color into two inside certain crystals under strict arrangements, and their polarizations emerge entwined. Test the pair in separated stations with settings chosen quickly and independently, and the shared statistics fall beyond what local hidden instructions could produce. That excess does not let messages outrun light speed, but it does allow new ways to distribute encryption keys. An eavesdropper's attempt to peek at the states introduces disturbances that honest parties can detect and quantify. Security comes from physics rather than secrecy of method. Detectors that register individual arrivals vary in design but share a goal. They must convert a tiny energy into a cascade large enough to read while rejecting false triggers from heat or noise. Avalanche devices multiply charge in a semiconductor when a packet is absorbed. Superconducting wires register a momentary loss of superconductivity when a packet breaks. Pairs that carry current with no resistance. Photomultipliers amplify electrons knocked loose from a surface across a series of diodes, turning one event into a measurable pulse. Each technology has strengths. Some excel at fast timing, some at high efficiency, some at very low false counts. Choosing among them depends on the scene: dim galaxies, faint fluorescence, or fast signals. In living eyes, receptors can respond to a handful of arrivals under careful conditions. The retinal cascade amplifies a single molecular change into an electrical signal sent along neural fibers. In the lab, experiments show that brief flashes near the threshold can be sensed by observers trained for darkness and quiet. In daily life, the brain requires more confidence and integrates over time. Yet the underlying sensitivity explains why starlight is visible away from cities and why slow movements at dusk still catch attention. Biology leans on the same discreteness that physics discovered in metals. Momentum from light also builds devices that move without conventional fuel. Highly reflective surfaces experience twice the push per arrival compared with absorbing ones. So engineers plan thin sails that harvest this pressure steadily. The acceleration is small, but it never ends, while illumination continues, and over long journeys that persistence accumulates into significant speed. Orientation control arises from tilting the sail or adjusting reflectivity in sections, transforming a uniform rain of packets into useful torque and thrust. The principle that shapes comet tails becomes a steering method for craft that carry no propellant mass. In laboratories that characterize delicate samples, gentle illumination avoids heating and chemical damage. Choosing a color that a specimen ignores reduces absorption while still allowing scattered packets to be counted. Time-gated detection separates early, superficial scatter from deeper, later paths, revealing layers without cutting or staining. Packet counting enables measurements at powers that barely raise temperature above ambient, preserving structure and function. The same discreteness that sets energy thresholds protects living material when light is chosen and timed with care. Entangled packets also extend measurement accuracy. When many share quantum relations, their combined statistics can outperform classical limits, squeezing uncertainty in one variable while allowing more in another. Interferometers that read tiny phase shifts can use such states to lower noise floors imposed by randomness in arrival times. This approach requires exquisite control of loss and disturbance, because entanglement is fragile, but progress continues as sources, fibers, and detectors improve. Packets that begin life as a pair can remain linked across long spools of glass, arriving ready to compare with sensitivities beyond ordinary beams. A brief metaphor may help the heart understand the restraint here. Imagine a fingertip tapping a glass so lightly the sound is almost private, yet the ring carries information about thickness and tension. Each arrival is that tap, a small and sufficient note. But facts must lead again. Energy is proportional to frequency by a universal constant. Momentum travels with the packet and transfers upon reflection and absorption. Counting events reveals patterns that would be hidden in steady flows. Correlations beyond classical bounds exist, but they do not ferry messages faster than light. Devices translate arrivals into voltages and timestamps, and those records become images, spectra, or keys. Another lantern appears, not bright, but reliable. The knowledge that tiny, discrete steps can build large, stable outcomes. A camera that counts few arrivals per pixel still builds a faithful picture given time. A sensor that registers rare molecules in exhaled breath still returns a diagnosis if the counting is honest and the background known. Precision grows from patience rather than force. The packet touches gently and recedes, yet the record remains, and the record is what the world can use. Between breath and breath, color begins as a pattern of energy our biology can read. 3 kinds of cone cells sample overlapping bands of wavelengths, and the brain compares their ratios to decide a hue. It does not measure absolute light with a single gauge. It weighs signals against each other and infers the surface beneath the illumination. This relative coding keeps familiar objects stable when the lamp changes. A red book near a window at noon and the same book under a warm bulb at dusk look like the same book, because perception balances the channels before it names the color. Rod cells favor dim scenes and pick up glittering contrasts when cones grow quiet. In that regime, hues compress toward a cooler cast, and the world softens into shape and brightness rather than fine tonal separations. Daylight at the ground is not a single recipe. Its spectral mix shifts with altitude, humidity, aerosols, and the path the sun takes across the air. At midday, in dry conditions, the distribution is broad and even. Close to storm fronts, the spectrum leans and dips, where water vapor and other gases absorb. These changes matter for cameras and for plants, because both depend on spectral content as well as intensity. Photographers adjust a white point to align sensor output with a chosen neutral reference. Leaves use pigments, tuned to bands that pass through air and canopy. The spectrum is a quietly moving target. Adaptation is the reason images and biology remain dependable while it moves. Artificial lighting adds variation of its own. Emission lines from gas discharge lamps build color from narrow spikes that repeat precisely with each cycle of power. Phosphor-based sources blend several peaks into a broader distribution, mimicking natural white, yet revealing their engineered structure in a spectrograph. Solid-state lamps assemble white by combining a diode and a down-converting layer, or by mixing several diodes with different peaks. The result may look similar to midday for many tasks, but paints and fabrics can react differently, because their reflectance curves interact with those peaks in ways that are invisible under a different lamp. That is why a dress selected in a shop can appear altered by the time it reaches a window. The difference is not the cloth. It is the handshake between lamp spectrum and material response. Color constancy in people depends on rapid recalibration. Pupil size changes over seconds to meter the incoming flux, and biochemical cycles in cones reset sensitivity with exposure. Neural circuits compare local patches to estimate the light falling on the scene, then discount it to find the underlying surface behavior. This computation is not perfect, but it is efficient and usually fast. When illumination shifts abruptly, a brief mismatch appears until the circuits settle. That settling time is part of why photographs feel harsher during sudden changes than the world does to the eye. The eye is already compensating while the camera is still measuring. Other species extend the visible palette with receptors placed beyond our range. Many songbirds include a fourth cone that reaches into the ultraviolet, revealing plumage marks that guide mate choice and social signals. Bees find landing patterns on petals that are invisible to us, yet obvious in a band their eyes can see. Those patterns reduce search time and increase accuracy in foraging. A partnership between plant and pollinator, written in wavelengths we cannot read, unaided. Some fish living near the surface compare polarized reflections to sort objects from ripples and glare. In snowfields, certain mammals see contrasts that help them find forage and avoid hazards, because their receptors respond to bands that reflect differently from crystals and lichen. Vision evolves to match tasks and habitats, adding or shifting channels where a small advantage persists across generations. Structure can create color even when pigments are absent. Microscale ridges, multi-layer stacks, and arrays of holes set distances comparable to wavelengths. When light reflects from these features, interference reinforces some bands and cancels others. The effect changes with angle because the path difference between layers changes as view direction changes. That is why some wings and shells shift through a spectrum as they move. These structural colors resist fading because the microstructure is stable long after many dyes would break down under exposure. Engineers borrow the principle in anti-counterfeiting foils that tilt through specific sequences, in strain sensors that change hue with deformation, and in architectural coatings that tune thermal load while maintaining a color impression. Surface finish influences color reading, even when pigments and structures are fixed. A glossy surface preserves directionality. A matte surface scatters broadly. Gloss emphasizes highlights and darks, exaggerating local contrast. Matte spreads brightness, softening transitions. The same paint can look deeper or flatter depending on microtexture, and the same hue can feel different depending on how it shares light with the room. Designers balance these properties to keep colors calm in sleep spaces and lively in places that ask for focus. The physics is simple scattering, the experience is mood-shaped by angles. Color temperature describes how the balance of long and short wavelengths within a white source compares to the glow of an ideal radiator at a particular temperature. Lower values feel warmer, higher values feel cooler. This description, though approximate for many lamps, tracks perception well enough to guide lighting choices. Short wavelength content plays a special role in signaling through retinal pathways that regulate circadian timing. Exposure earlier in the day supports alertness by shifting internal clocks toward daytime behavior. Exposure at night can delay sleepiness by sending a daytime message to the brain's timing centers. Filters that reduce short wavelength content in the evening help synchronize rest, but intensity and timing also matter. A small amount of the wrong light at the wrong moment can be disruptive, and a moderate amount at the right moment can stabilize rhythm. In galleries and studios, spectral balance affects how pigments mix. Two paints may match under one lamp and diverge under another, because their spectral reflectance curves are not identical, even when they produce the same trichromatic response under a specific light. This metamerism becomes important when making reproductions or selecting materials for adjacent surfaces. Standards specify test sources and indices that rate how faithfully a lamp reveals colors compared with benchmarks. These ratings do not capture every nuance, but they reduce surprises by quantifying how a light renders a set of typical samples. Choosing high-fidelity sources in places where color judgment matters prevents costly misreadings and lowers visual stress. Children learn color words early, but the underlying skill is learning categories based on experience rather than memorizing wavelength maps. Cultures divide the spectrum into named regions differently, yet observers converge on similar focal examples of each category. That convergence suggests that biology sets limits, while language and environment place labels within those bounds. Even within one person, categories shift with context. A tile that appears neutral against one wall may look faintly tinted against another. The tile did not change, but the comparison set did, and the brain anchored the scene to the new average. Understanding this fluidity decreases frustration when objects won't match. They are not inconsistent. Our calibration is active and local. Rain-wet streets, winter sky, shaded rooms, each setting cuts or adds slices of spectrum in characteristic ways. Vision handles these smoothly until a camera enters the scene and fixes a frame. Then the difference between adaptation and measurement becomes clear. Cameras may record what the light was. Eyes remember what the surfaces are most likely to be. When photograph and memory disagree, the answer is not error in either system. It is a mismatch in purpose. Adjusting white balance, using a gray card, or choosing a light that matches the intended context eases the gap. In quiet terms, color is a compact agreement between available photons, receptive cells, and expectations learned over time. The science is modest in its statements. Cones compare, rods gather. Adaptation is quick but not instantaneous. Lamps have specific spectra. Materials have specific responses. Textures change directionality, and structures can write hue without dye. Yet from that modesty, stable daily experience emerges. You recognize your blanket at sunrise and buy a bedside lamp. You read ink on paper at noon and at midnight without relearning the alphabet of chroma. A small metaphor may rest beside these facts like a hand on a railing. Color is a chord, not a single note. The instruments are the cones, the ear is the brain, and the hall is the room and its lamp. Change the hall, and the chord feels different, but the score on the page remains. That is enough image. The through line is practical and human. Better sleep comes when evening light is gentle, in spectrum, and low in intensity. Better work comes when morning light is bright and broadly balanced. Better comfort comes when rooms avoid sharp shifts that ask the eye to recalibrate with every step. As the room grows quieter, this balance becomes companionship. The world does not insist on one fixed illumination for you to feel at home. It meets you halfway, allowing constancy through comparison and meaning through learned expectations. Vision is a practiced listener, translating variable songs into familiar names. Trust that practice. It is why your notebook looks like your notebook, even when a cloud moves across the window. It is why a bedside story feels the same beneath a lamp and beneath a sky. And it is why a gentle, thoughtful light at the end of the day helps thought itself settle, while the colors you know stand close by, unchanged in spirit even as the spectrum bends around them. Light sketches straight lines until a boundary asks it to choose. At a smooth surface, The incoming path and the departing path keep equal angles on opposite sides of an imaginary perpendicular. This balance is not a taste for symmetry. It follows from a deeper rule that favors routes of stationary travel time. When the surface turns from shiny to transparent, direction changes in a second way. The beam bends as it enters, guided by how quickly phase advances inside the new material compared with the old. An index summarizes that change in pace. Pair the signs of the angles with the indices on each side, and the ratio holds with quiet reliability. Those trigonometric partners explain why a coin looks displaced at the bottom of a clear bowl, why a straw seems kinked at the waterline, and why polished lenses can steer rays to a shared point. Curvature turns local rules into images. A concave mirror collects nearly parallel paths and folds them inward toward a focus. A convex mirror sends them outward, shrinking scenes for a wider view. Neither is perfect when shaped as a simple sphere. Rays far from the axis land in slightly different places than rays near the center, an imperfection called spherical aberration. A paraboloid corrects that flaw for distant sources, which is why deep dishes for telescopes and antennas adopt that form. On the transmissive side, a single lens can converge or diverge rays, but thickness, glass type, and surface shape determine how well colors agree at the same plane. Designers combine elements made from different glasses, so dispersion in one cancels dispersion in another, letting red and blue come to rest together. The result is clarity that holds across the spectrum rather than at one favored shade. Light inside a dense medium encounters its own boundary choice when approaching a face beyond a steep angle. Past a certain tilt, there is no refracted path that meets the angle requirements set by Snell's law, and every bit of the wave turns back. This is total internal reflection, and it traps rays inside transparent rods and sheets with astonishing fidelity. Glass fibers use it to shepherd signals around bends and through long spans, provided the curves are gentle and the core stays pristine. At the microscale, raindrops use the same rule to trap and redirect sunlight, contributing to the complex caustics that dance on wet pavement and to bright bands formed by multiple internal bounces. In instruments, prisms exploit total internal reflection to fold optical paths compactly with little loss. Binoculars use paired prisms to invert images and shorten barrels without wasting light on metallic mirrors that would absorb a portion at each bounce. A surface can be persuaded to ignore reflection through structure measured in fractions of a wavelength. A single film 1/4 of a target wavelength thick, with an index nestled between air and glass, sends a reflected wave from its top face that interferes destructively with the reflection from the substrate. If the thickness and indices are tuned precisely, the glare at that color softens dramatically. Stack many films with carefully chosen thicknesses and indices, and the suppression spreads across a broad band. Camera lenses carry such multi-layer coatings, often visible as faint hues when held to a lamp. The colors on the glass do not announce image tint. They reveal which residual reflections remain outside the target band. In the opposite direction, a different stack of films can reinforce reflection at certain wavelengths, creating mirrors with nearly perfect return in narrow bands. Laser cavities depend on such dielectric mirrors to confine light thousands of times, building up intensity while losing almost nothing at each encounter with a surface. Not every design uses discrete layers. Some use textures that grade index gradually from air's value to the value inside the substrate. This moth-eye approach borrows from the microstructure of nocturnal insects that avoid reflections which would betray them to predators. The tapered array of sub-wavelength features lets the wave ease into the material without a sharp jump, lowering return across a wide band and a wide range of angles. Solar panels benefit from such textures because every reflected photon is one lost opportunity. The world outside our windows carries similar lessons. Frosted glass scatters broadly, lowering glare by sending light outward in many directions from tiny surface roughness, while polished glass preserves direction and specular highlights. Shape and layout do more than form sharp points. It organizes how entire fields move through volumes. Gradient index, GRIN, materials change refractive index with position, bending rays continuously, rather than at a discrete boundary. A cylindrical rod with higher index at its center than at its edges can focus without any curved surface at all. In certain designs, a quarter turn of the rod's internal index profile brings parallel rays to a focus on the far side, useful for compact endoscopes and fiber couplers, where space is tight and precision matters. Glassmakers and polymer chemists craft these profiles through controlled diffusion and careful curing, turning a bulk piece into a quiet lens whose power lies in its interior rather than on its face. Prisms serve across scales, from desk instruments to mountain observatories. Split a white beam, and each color departs at a slightly different angle, because index depends on frequency in most materials. This dispersion is small in ordinary glass, but sufficient to fan colors into a spectrum. Place a prism pair with contrary orientations, and dispersion can be compensated or intensified as needed for a particular instrument. In spectroscopy, accuracy depends on how precisely the angles are known and how stable the prism remains with temperature. In binoculars and periscopes, a different family of prisms, poro and roof designs flip and shift images so that upright views emerge from inverted optics within compact housings. Corner cube reflectors, a special prism arrangement, return beams to their source, regardless of how the reflector is rotated, a property used to mark distances on the Moon and to align machinery on Earth with sub-millimeter confidence. Air, too, has refractive structure. Density changes with temperature and pressure, and index changes with density. On hot ground, steep gradients bend rays upward, mapping sky into a shimmering patch that looks like water. Over cold seas or ice, inversions bend rays downward, lifting distant horizons into stacked, wavering images. These are not tricks. They are lawful paths through a medium whose properties vary smoothly with height. The most elaborate forms, sometimes called fata morgana, create terraces of reality in the sky, as many layers each add a slight turn. Mariners learn to distrust single sightings when the air stratified. Surveyors correct for bending by modeling the atmosphere's state or by measuring in conditions when gradients are small and steady. When particles and crystals fill air, refraction draws rings and arcs around the sun and moon. Plate-shaped ice, drifting with preferred orientations, creates bright side spots at a fixed distance from the sun, known as parhelia. Columnar crystals form arcs that curve and intersect in halos, whose geometry identifies which shapes are falling and how they are aligned. These displays are skyborne diagrams of microphysics, visible to any walker who looks near the bright source with care. The same rays that bend on a desk prism bend in the troposphere. Only the facets are natural, and the detector is your eye. Reflection has subtleties beyond angle in equals angle out. At the boundary between dielectric materials, the fraction reflected depends on polarization and angle. For a certain approach angle, one orientation sees almost no reflection at all. This Brewster condition allows polarized light to emerge from reflections off non-metallic surfaces. It also provides a way to build lasers that oscillate in a preferred polarization by inserting a tilted plate in the cavity that favors one orientation with lower loss. Designers take advantage of these angular preferences to reduce stray light in instruments and to pick off small fractions of beams without damaging delicate coatings. Metals handle reflection differently. Their free electrons respond quickly and strongly to the oscillating electric field, setting up currents that cancel the field inside to considerable depth. The result is high reflectivity across broad bands, especially at longer wavelengths. At shorter wavelengths, where interband transitions occur, reflectivity can dip and colors emerge. That is why gold and copper look warm rather than neutral. Thin metal films behave in intermediate ways, transmitting some light while reflecting the rest, and their properties change with thickness and microstructure. Designers choose between metals and dielectrics based on bandwidth, durability, scattering, tolerance, and thermal load. Refraction in crystals sometimes splits a single incoming direction into two outgoing directions because the speed of light depends on polarization, as well as direction inside anisotropic lattices. This birefringence reveals itself when a clear calcite fragment placed over a printed line produces a double image. Rotate the crystal, and the images dance relative to one another. Instruments use this property in wave plates that shift relative phase between polarization components, allowing rotation of orientation without loss. In microscopy, crossed polarizers and birefringent samples reveal stress patterns and crystalline order that would otherwise remain invisible. Designers of objectives must tame not just color focus but field curvature, coma, astigmatism, and distortion. These names are the fingerprints of how rays at different heights and angles disagree about where the best image lies. Symmetry helps. So does pairing positive and negative powers. As lenses grow faster, that is, as their openings widen relative to their focal lengths, aberrations swell unless carefully balanced by spheres and special glasses. The aim is not perfection under one arrangement, but acceptable performance across a field and across focus for the intended use. A lens for portraits has different priorities than a lens for stars. The ray rules are the same. The compromises are human. There is a humane steadiness in all this. Rays choose paths that make sense when time is tallied honestly. Surfaces and volumes nudge them according to rules that fit handbooks and sky displays alike. If you want a brief image to lean on between these facts, consider a path traced by a patient walker through hills, taking the route that is neither showy nor slow, simply consistent with the terrain. Then return to the clarity that matters for making and seeing. Smooth faces reflect with equality. Transparent bodies bend with ratios. Layers cancel with quarter-wave care. Textures grade gently to ease entry. And gradients in air draw scenes into places where they do not belong. The comfort here is predictability without stiffness. You can design, correct, and trust. You can look up and read the sky. You can set a lens and be sure that what should align will do so. And as the mind grows quieter, that exactness can feel like the softest kind of company, a map you do not need to hold, because the world holds it for you. Waves meet, and brightness answers with arithmetic. Where crests arrive together, light strengthens. Where a crest meets a trough, light thins to near nothing. Interference is not a decoration. It is how fields add in the world. The eye records intensity which follows the square of amplitude, so tiny phase shifts create large contrasts. A path just a fraction of a wavelength longer can darken a spot that was bright a moment before. Two openings, one screen, and a steady source already reveal the rule. The spacing between bright and dark bands depends on wavelength, on how far the openings lie apart, and on how distant the screen sits. Adjust any one of these quietly, and the whole pattern breathes wider or tighter in response. An interferometer refines this playground into a measuring tool. Split one beam into two paths, send them away, and bring them back together. If the returning phases match, intensity rises. If they oppose, intensity falls. Count how the output sways while a mirror moves by known steps, and length reveals itself with precision beyond ordinary rulers. A Michelson layout does this with simple symmetry. One arm reflects from a movable mirror, the other from a fixed reference. When the moving mirror advances by half a wavelength, a bright fringe becomes dark at the detector. Track many such changes, and you read distances in slices of a wave, not in millimeters on a stick. The same principle monitors surface flatness, lens figure, and thin layer thickness with calm certainty, because phase is honest about distance. Air never stands perfectly still, and neither do supports and hands. Interferometers answer these realities with designs that reject common disturbances. Some fold both paths through nearly the same air, subtracting shared fluctuations. Others use reference cavities that anchor phase to optical lengths inside stable materials. Vibration isolation, temperature control, and short exposure times help pull signal forward while background drifts fade. Stability becomes an ally rather than a demand. With that care, phase reveals motions smaller than an atom's size, and the record of those motions carries meaning in fields as distant as seismology and microfabrication. Diffraction is the other face of the wave, the spreading that follows when a field squeezes through a limited opening. No aperture, however sharp, can throw a perfect point beyond. A circular stop paints a core of light surrounded by rings. The size of that core sets a basic limit on how close 2 points in a scene can be before their images merge into one. Increase the opening, and the core shrinks. Use shorter wavelengths, and it shrinks again. This relationship defines what astronomers can separate in the sky, and what microscopists can distinguish in cells. Smooth polishing cannot outwit it. Clever design must respect it. Edge shape and pupil weighting can soften rings and shift energy inward. Apodization, tapering the transmitted amplitude across the aperture, reduces side lobes at the cost of a larger core. Some telescopes mask their pupils to form more favorable patterns for particular tasks, such as isolating faint companions near bright stars. Coronagraphs add occulting elements and phase plates to cancel starlight at the image plane while leaving nearby fields accessible. The mathematics guiding these efforts belongs to Fourier optics. Lenses relate patterns in the pupil to patterns in the focal plane by a transform that maps angle into position, and vice versa. The image you see is a filtered version of spatial frequencies present in the object, weighted by how the system passes or suppresses those frequencies. When distance and scale move into the far field, diffraction patterns simplify into clean, angular maps. A line grating sends different colors to different angles, like a fan whose ribs are marked by integer orders. Groove spacing controls the spread. Narrow spacing yields broad dispersion. Wide spacing keeps colors close. Blaze angles steer energy into favored orders by aligning facets to reflect strongly toward chosen directions. Spectrographs rely on these rules to place faint lines on detectors with space between them, turning angles into wavelengths and intensities into counts. For stability, gratings must resist humidity and temperature shifts. For efficiency, groove shape must be regular down to submicrometer scales. Volume holographic gratings store periodic patterns throughout a material's depth rather than just on a surface. Light diffracts via Bragg-like conditions that select a narrow band of wavelengths and angles. These elements act as spectral filters, notch rejectors, or beam combiners with high stability and narrow bandwidth. Their selectivity helps instruments pick a single line from a crowded spectrum or remove a strong background without harming neighboring features. The three-dimensional nature of the grating confers resilience against surface wear and allows tuning by temperature or small mechanical strains. Interference writes images onto media in holography. A reference beam and a scene beam meet on a plate and create a pattern that encodes phase and amplitude. Later, illuminating the plate with a beam related to the original reference reconstructs a wavefront that appears to come from the scene again, complete with parallax when you move your head. The plate does not store a picture of brightness alone. It stores the interference pattern that regenerates the field itself. Stability during recording is crucial, because any drift blurs the fine fringes that carry depth information. Even breath near the setup can shift air enough to wash detail away. In exchange for that care, a thin film of emulsion can replay a three-dimensional memory that feels present rather than printed. Near-field diffraction behaves differently from the far field. Close to the object, the wave has not yet simplified into clean, angular components, and features in this Fresnel regime show ripples and edge effects that depend on exact distance as well as shape. Zone plates exploit this region by carving concentric rings whose widths follow a rule that brings light to a focus through constructive interference. They act like lenses without curvature or bulk, especially effective for wavelengths where glass would absorb too strongly to make standard optics practical. In the soft X-ray band, zone plates form images of tiny structures in materials and biological samples, using interference as the focusing agent when conventional refractors would fail. Crystals extend interference into structure determination. A regular array of atoms scatters incoming waves into specific directions that satisfy lattice spacing conditions. The resulting pattern of spots on a detector encodes the distances and orientations of planes within the crystal. By rotating the sample and recording many such patterns, a three-dimensional map emerges of where atoms sit within the unit cell. X-rays, electrons, and neutrons each interact differently and reveal different aspects: electron density, charge distribution, or nuclear positions. These patterns are not images in the everyday sense, but they are deeply informative. From them, the shapes of proteins, the phases of alloys, and the strain fields of thin films are inferred with precision sufficient to guide chemistry and medicine. Speckle appears whenever coherent light scatters from a rough surface or a volume with many small inhomogeneities. The field at the detector is a sum of many paths with random phases, and intensity varies granularly as those sums lean constructive or destructive over small movements. To eyes and cameras, speckle looks like noise, yet the grain carries information about motion, deformation, and flow. Measure how the speckle pattern changes over milliseconds, and you can infer vibration in a machine part or blood perfusion in tissue. Average many uncorrelated speckle realizations over time or slightly varying angles, and the grain washes out, leaving the underlying scene. Both options, reading speckle or defeating it, are useful, depending on the job. Moiré patterns arise when two repetitive structures overlay with slight differences in spacing or angle. The result is a slow beat pattern that magnifies small misalignments into visible bands. Engineers use this sensitivity to measure small rotations and strains. Photographers sometimes see moiré when sensors meet fine fabrics. Anti-aliasing filters blur just enough to hide the beat. Interference lies beneath this, too, the sum of two similar spatial frequencies, forming a difference frequency that the eye can follow. What seems like a nuisance becomes a ruler when used deliberately. When waves meet boundaries with differing thicknesses, interference paints maps across surfaces. A thin coating applied unevenly will show color bands that reveal thickness variations down to tens of nanometers. Makers exploit this as a diagnostic during polishing and deposition, watching fringes crawl as layers reach their targets. Transparent parallel plates make an étalon, light bouncing between the inner faces, produces transmission peaks at regularly spaced wavelengths that depend on thickness and index. By tilting or stretching the etalon, one can tune which wavelength passes, creating filters of high finesse used in astronomy and laser stabilization. Interference also stabilizes clocks and locks frequencies. A cavity with two mirrors supports standing waves at frequencies that fit an integer number of half wavelengths between the mirrors. When a laser's frequency matches one of these cavity modes, transmission soars. Scanning the cavity length reveals fringes that beat with the laser's drift, and feedback holds the laser on a chosen feature. With a second cavity or a frequency comb to compare against, absolute frequency can be counted and linked to standards. The power of this control reaches into navigation and tests of physical laws, because time and frequency live at the heart of measurement. Diffraction's limits inspire workarounds that remain faithful to physics. In imaging, patterned illumination shifts fine details into bands the system can pass, and computational steps move them back to their rightful places at higher resolution. In antenna arrays and telescope networks, signals from separated apertures combine in software to synthesize a larger, effective opening. Baselines set which spatial frequencies can be sampled. Earth's rotation fills coverage gracefully. Although the idea belongs to radio ranges most comfortably, optical versions exist with careful delay compensation. Interference, again, is the bridge. Separate measurements become one image because phases can be aligned and added like singers holding the same quiet pitch. Edges and slits carry their own signatures. A single narrow slit forms a broad stripe on a distant screen, with intensity falling off as angle increases. Two slits multiply that single slit envelope by a fine comb of fringes. Widen the slits, and the envelope narrows while the fringe spacing stays set by the separation. Replace slits with a square aperture, and the pattern becomes a cross with arms that thin as you move away from the center. Round holes deliver circular rings. Understanding these basic shapes helps an observer recognize causes when a photograph shows strange halos or a telescope image exhibits spikes around bright points. The pattern traces back to the geometry of the opening, a fingerprint that does not lie. In liquids and gases, index fluctuations from heat and flow scatter coherent light into shimmering caustics. Shadow graph and Schlieren methods visualize these changes, turning invisible currents into patterns that betray shock waves, boundary layers, and convection cells. A knife edge in a focal plane converts small deviations in beam angle into brightness changes on a camera, revealing gradients in density as swirls and plumes. These techniques make airflow around wings visible, show heat rising from candle flames, and help refine designs from lab burners to supersonic nozzles. Again, it is phase becoming intensity through a gentle trick of optics, converting difficult-to-measure variations into clear pictures. Interference is sensitive to wavelength, so using multiple colors can separate overlapping effects. A metrology system may cycle through several bands to resolve ambiguities when many fringes appear similar. Chromatic strategies also reduce sensitivity to unintended etalon effects in windows and sensors by averaging out narrow features. Polychromatic light smears fine fringes, unless steps are taken to preserve coherence over the path length. Designers choose balance: narrow bands for sharp contrast, broader bands for robustness against spurious patterns. The goal governs the spectrum, not habit. A brief metaphor can rest here like a single feather on a ledge. Interference is a weaving loom where threads cross at precise intervals, and the cloth shows a pattern only when the crossings agree. Then let the facts lead again. Two paths add as amplitudes. Intensity follows the square. Phase differences come from distance, index, and angle. Aperture size sets a core of blur that no polishing erases. Gratings trade spacing for dispersion. Holography stores a field by writing its interference with a reference. Speckle is random phase made visible. It can be read or averaged away. Moire magnifies small spacing or angle differences into clear bands. Etalons pass a comb of wavelengths, and cavities tame frequency drift by resonance. Another feeling returns, quiet and useful. Patterns are not accidents. They are signatures, dependable as a slow breath in a dim room. A measured fringe can be trusted as a mark of distance. A widened ring can be trusted as a sign of a small opening. A speckle field that trembles can be trusted as an indicator of motion too small to see otherwise. When sleep gathers, that trust is soothing. The world will behave the same when morning comes. The stripes and rings and grains will obey their simple rules, and from those rules, instruments will keep reading and making. The night is full of patterns that require no effort to persist. We only need calm eyes and steady hearts to understand that their order is always there, waiting quietly beneath the surface of brightness. Every warm thing glows, whether eyes notice or not. Temperature sets charges in motion inside matter, and those motions launch electromagnetic waves, whose mix depends on how energy is shared among available modes. Imagine an ideal surface with no preferred color and no internal mirrors, one that swallows every arriving photon and radiates only according to temperature. Physicists call it a blackbody. Its spectrum rises from long wavelengths, swells to a smooth crest, then falls toward shorter waves with a tail set by quantum statistics. As heating continues, the peak shifts toward shorter wavelengths, and total radiated power rises very steeply with temperature. That rise is not a guess. It is a precise relationship that makes furnaces, stars, and quiet embers legible at a glance. Real materials sing close to this tune but add their own timbre. A sooted cavity or matte ceramic may radiate efficiently across wide bands. A polished metal reflects much of the long-wave energy and emits less emissivity. The fraction of ideal blackbody output a surface actually emits varies with wavelength, angle, and polarization. The number is never truly single, though practical averages often predict performance well. A coiled filament glows because its lattice, heated hard, spews a broad spectrum that happens to include enough visible light for human cones to respond. A stovetop coil, though cooler, radiates mostly beyond sight. You feel its presence long before you see orange. Kirchhoff's law ties emission to absorption at thermal equilibrium. A good absorber at a given wavelength is a good emitter at that same wavelength. That is why a dark, rough cavity radiates so well, and a mirror-bright surface does not. As heating increases, the visible impression changes from a dull red through orange to a near white blend, not because pigments form, but because the spectrum's peak slides while the whole curve lifts. Color becomes temperature's quiet accent rather than its essence, a readable hint in a larger field of invisible power. Thermal radiation powered early household lamps. A tungsten filament, cushioned by inert gas, was driven until it glowed. The result was continuous spectrum and generous color rendering, because many wavelengths mixed together. The cost was waste, most energy left as infrared that eyes cannot use. Modern lighting shifted toward electronic transitions and phosphors that create chosen wavelengths more efficiently. Yet glow physics remains fundamental wherever heat runs high. Molten metal announces its condition by hue. Pottery kilns reveal their state through the chamber's light. Foundry workers still read warmth with eyes trained by years of practice. Cameras tuned to longer wavelengths turn this glow into numbers. They do not feel heat, They count photons and compare brightness at several bands to a modeled spectrum to infer temperature without touch. Maintenance crews find failing bearings and overloaded breakers by their subtle excesses over background. Clinicians map inflammation where blood flow and metabolism lift skin temperature slightly. Surveyors trace roof leaks at dawn when surroundings are even and contrasts are clean. Accuracy depends on calibration and on knowing the surface's emissivity. A shiny pipe and a painted wall at the same temperature will look different unless the instrument accounts for their signatures. At low temperatures, the radiated power dwindles quickly, and detection becomes a quiet art. Instruments that watch the far infrared must chill themselves so their own warmth does not drown the scene. Detectors sit behind windows that pass the chosen band but block stray radiation. Baffles and shields surround optics cooled far below room temperature so that self-glow falls away. Space observatories carry radiator panels that face deep space, sipping heat from instruments until they rest at stable, cold set points. Without this discipline, a telescope would mostly measure itself. Selective emitters adjust the rules by sculpting surfaces at scales smaller than a wavelength. Arrays of microscopic cavities and ridges can absorb strongly within chosen bands while reflecting elsewhere. Under a clear, dry sky, there is a window in the mid-infrared where air is relatively transparent. Surfaces engineered to radiate efficiently in that window while reflecting much of the sun's visible and near-infrared light can cool below ambient during the day without power. Roof films and coatings using this principle lower peak temperatures and ease energy demand. At night, the same pathway lets heat slide gently from stone and soil into the dark, setting dew on leaves even when air remains slightly warmer. Materials science widens the palette further. Ceramic oxides, doped semiconductors, and metallic meshes tune emissivity with direction, favoring emission toward the sky while muting it toward warm surroundings. Microtextures can also polarize thermal light at glancing views. The alignment of grooves and grains biases the orientation of the emitted field. Engineers exploit that bias to tailor heat rejection on spacecraft. Without air to carry heat away, satellites maintain temperature by balancing sunlight, shade, and radiation to the cold sink of space. Louvers change effective emissivity with angle. High emissivity panels point to darkness. Low emissivity faces turn toward warm structure. The exchange is all light, yet it governs survival. Astrophysics reads thermal spectra to judge temperatures of stars and dust. A star's overall color indicates an effective surface temperature, while small departures from the ideal reveal gases in outer layers that imprint characteristic absorption bands. Dust warmed by starlight glows brightly in long-wave bands, outlining the ridges where new suns gather from cold clouds. To see these signals, observatories sit on high, fly on balloons, or orbit beyond air altogether. Water vapor and carbon dioxide in the lower atmosphere absorb strongly in many of these bands. Getting above them turns a blocked symphony into a quiet, readable score. Radiative transfer, the careful accounting of emission, absorption, and scattering along a path, ties optics to heat flow. In furnaces, hot gases and soot carve valleys in the spectrum that complicate how energy reaches the walls and the load. Models track which wavelengths escape, which are trapped, and how surfaces re-emit what they absorb. In planetary atmospheres, gases allow much sunlight to reach the ground while hindering the planet's attempt to radiate heat back outward. The balance sets surface temperature and drives weather. Clouds, aerosols, and surface texture all shift the outcome by redirecting the radiation field in ways that instruments can measure and simple intuition often misses. Emissivity is a material's signature in this exchange. It shifts with wavelength, angle, and polarization, so a single value rarely captures the whole story. Still, practical averages over relevant bands and directions guide design. Black, anodized aluminum behaves nearly like a perfect radiator in the thermal infrared, while reflecting a useful fraction of sunlight. Polished metals show the opposite tendency, reflecting strongly at long wavelengths and demanding care to avoid trapping heat where it should be shed. Textured paints lower glare and raise thermal output. Thin films can stack to create surfaces that emit in one band and reflect in another, allowing thermal control without heavy mass. Measurement requires honesty about the environment. Reflections from sky, ground, and the instrument itself can bias readings if ignored. Weather matters. Humidity narrows the mid-infrared window, and wind alters surface temperature independent of radiation. Time matters. Backgrounds change rapidly around sunrise and sunset as ground and sky trade roles as the warmer partner. Good practice subtracts backgrounds, calibrates emissivity with known references, and states uncertainty, so decisions match the confidence the data deserves. Precision here is not only a number, it is an agreed understanding of conditions. Thermal light also belongs to safety. At very high temperatures, significant energy enters shorter wavelengths that can injure tissue and stress electronics. Shields and filters intercept those bands while letting process heat escape. Glass that blocks ultraviolet protects workers near molten baths. Coatings that reflect near-infrared guard sensors in kilns. At the other extreme, clear sky cooling can lower exposed surfaces below air temperature and invite frost. Growers spray water or deploy covers to buffer plants against that radiative dip. The fix is simple because the cause is simple. The sky is a cold sink, and an exposed leaf sees it directly. A small metaphor can rest briefly beside these facts, then step aside. Temperature speaks in a light no one needs to name. Low voices hum in long waves. Higher voices rise into brighter notes. The chorus grows louder, much faster than the conductor's hand appears to move. Enough image. The anchors remain steady. Spectral peaks drift toward shorter wavelengths as heating grows. Total radiated power climbs sharply with temperature. Emissivity bends reality away from the ideal in ways that can be measured and used. Instruments read glow to infer temperature at a distance, turning warmth into data without touch. There is tenderness in that steadiness. Thermal light neither flatters nor hides. It states exactly what statistics and structure allow, then fades when energy thins. Perhaps that is why its presence feels calm. It never rushes your attention or begs belief. It simply says, here is the state of things, honest and complete. And as evening deepens, that faithfulness becomes a soft companion. The glow slips into background, the rules keep working, and breath matches their quiet rhythm. If you listen for it, you can almost feel the room balancing with space beyond the roof, a gentle, radiant conversation that continues whether anyone notices or not. Air is not empty. It is a field of tiny partners that nudge passing light. When the particles doing the nudging are much smaller than the wavelength, the strength of each nudge scales steeply with color, sending shorter wavelengths aside more than longer ones. This selective deflection distributes blue across the dome, while leaving the direct solar beam less blue by comparison. Look far across open distance and the contrast softens, because the same preference favors a gentle wash of short wavelength scatter between you and the far ridge. The effect grows with path length. More air, more chances for deflection, more pastel in the view. When particles rival the wavelength or exceed it, the rules change. The color dependence weakens, and the angular pattern shifts towards strong forward lobe and secondary features that depend on size and shape. Water droplets in clouds are in this regime. They scatter efficiently across the visible band and across wide angles, so scenes under overcast seem lit from every direction. Shadows fade because illumination arrives not as a beam but as a field. An overcast day is a giant diffuser hung across the sky, a natural light box that reveals texture without harsh edges. Fog is similar but closer. The droplets between an observer and the scene redirect light toward the eye and away from it at once, reducing contrast more than total brightness. Distant objects wash into the background because the forward scattered veil overlays their edges. Vehicle lamps can make the problem worse if their beams send too much light straight into the droplet field in the line of sight. Patterns optimized for mist lower backscatter toward the driver, while maintaining enough forward energy to reach reflective signs and road surfaces. The design goal is simple: help the eye by avoiding light returned straight from the veil of scatter at short range. Instruments read scattering to retrieve particle sizes and concentrations, measure how brightness varies with angle in several colors, solve the inverse problem that ties those curves to size distributions, and the aerosol field emerges without touching a grain. Satellites view the same air in multiple bands and polarizations, turning the way the sky's electric field aligns into estimates of composition. Polarization is powerful because it carries memory of the last deflection. Molecules scatter with a strong preference for planes perpendicular to the incoming electric field. Larger particles soften and complicate that pattern. The differences allow retrieval algorithms to separate smoke from dust and sea salt from pollution across wide swaths each day. Raindrops and drizzle add structure at small angles. Beneath a sun just masked by thin cloud, you might notice a bright circular region around the source and a soft plume extending away. Those are forward scattering signatures of near uniform droplets, patterns that narrow as drops grow. At the anti-solar point, exactly opposite the sun mist, can produce a colored ring around your shadow called a glory, born from multiple internal deflections and surface waves skimming around droplets. These features are not always present because size, uniformity, and geometry must align, but when they appear, they are field notes written by water in air. Underwater, scattering and absorption reshape scenes quickly. As depth increases, longer wavelengths fade because pigments in water remove them efficiently, while shorter wavelengths penetrate but scatter. Wide-angle photographs at depth look monochrome because path length robs the scene of reds and yellows. Divers bring lamps close to subjects to return familiar hues. Cameras balance channels to restore a natural look, but the correction must respect distance. Illuminate too far from the lens, and the same forward scatter that softens fog will wash the frame with backscatter. Good practice brings light near the camera axis, or uses two slanted beams to light the subject from the sides, while keeping the direct backscatter cone narrow. Rivers and lakes hold their own signatures. Fine mineral suspensions scattering broadly give turquoise and jade tones that shift with load. Organic matter absorbs more in the blue, tilting the spectrum deeper toward amber. Remote instruments read these spectral differences to estimate suspended sediment and chlorophyll, and to monitor blooms in near real time. Angle matters. Water's surface reflects strongly at shallow view angles, polarizing the reflection and adding glare that hides what lies beneath. Polarizing filters tame that reflection by blocking one orientation, improving visibility into the column when the surface is calm enough for a clean subtraction. Planetary atmospheres reveal themselves through scattering phase curves, plots of reflected brightness versus angle between star, planet, and observer. Thick hazes of complex organics, like those surrounding some moons and distant worlds, mute color and flatten polarization. High clouds of crystals produce sharp peaks and dips tied to particle habits. By fitting these curves, astronomers infer cloud heights, particle sizes, and even vertical layering without sending probes. On Earth, skylight polarization draws a wide, invisible band across the dome that rotates with the sun's position. Many insects detect that band directly and use it to keep course when landmarks vanish. A biological compass set by scattering rather than magnetism. Engineers tune scattering for human tasks. Microbeads, embedded in paints and coatings, spread light to hide surface flaws and reduce glare. Nanopores, etched into glass, reduce reflection by grading the refractive index from air to solid, easing entry and lowering surface brightness without altering transmission through the bulk. Display makers tailor bead size and concentration in diffusion films to create uniform backlights that preserve directionality for viewing angles while preventing banding. In agriculture, greenhouse covers that diffuse light feed lower leaves more evenly, increasing photosynthetic efficiency by avoiding hot spots and dark stripes beneath support structures. Visibility metrics quantify what eyes report informally. Contrast threshold models relate background luminance, target size, and scatter field to the smallest difference detectable. Those models feed standards for runway lights, road signs, and cabin displays. Safety does not rely on hope. It relies on numbers woven from how haze steals contrast and how illumination restores it. In design, the goal is rarely to eliminate scatter, because air and glass will not oblige. The goal is to shape it so that the eye's edge detectors and color channels receive an honest signal. In medicine and materials, controlled scatter becomes a probe. Optical coherence methods treat tissue as a layered, scattering medium and read faint echoes from within without cutting. Diffuse optical tomography pushes light through centimeters of tissue and, by solving an inverse scattering problem, maps changes in absorption and scatter that track physiology. In industrial inspection, structured light patterns projected on surfaces scatter back with distortions that encode dents, seams, and warps. The mathematics is similar across fields. Model how light moves, measure what returns, adjust the model until prediction and observation agree within known bounds. In the atmosphere, urban haze couples physics with policy. Aerosol composition shifts with sources and weather, altering not only visibility but also how much sunlight reaches the ground and how much heat escapes to space at night. Some particles cool by reflecting sunlight, others warm by absorbing it and heating the air directly. Measurements that separate scattering from absorption at multiple wavelengths establish which process dominates in a given episode. Those facts feed decisions about emission controls, because changing the particle mix changes not only air quality at street level, but also regional energy balance. A brief image may rest for a single line, then step aside. Scatter is a soft veil that chooses which colors to let through. The veil is not capricious. It is ruled by size, shape, composition, and angle. Understanding those rulers gives control back to observers and builders. Choose lamp spectra and beam patterns for fog. Choose coatings that silence glare at the angles that matter. Choose polarizers when water hides the riverbed. Choose camera distances and lighting geometry underwater so backscatter does not dominate the frame. Clarity is rarely a gift. It is a collaboration. Air, droplets, dust, and light negotiate a path to your eyes. If you know the terms, you can help the negotiation favor what you need to see. For sleep, the comfort is simple. The world is not blurred by mystery. It is softened by rules. Those rules are steady enough to trust. When morning comes and the hills look washed, you will know it is the path length talking. When an evening storm turns the horizon bronze, you will know it is particle size and sun angle in quiet partnership. And when a room glows evenly under a dome of cloud, you will know that the sky is doing what any good diffuser does, sharing light with every corner, without hurry, without drama. with kindness spread thin and wide. Predictability in phase is what coherence means. If, along a beam, the wave's peaks and troughs keep a stable relationship over time, the light is temporally coherent. If, across the beam's width, phases align so that different parts of the wavefront agree, the light is spatially coherent. Broad spectrum sources provide many slightly different frequencies at once, so their phase relationships wander quickly, and their coherence length, the distance over which phase remains predictable, is short. Narrow spectrum sources hold phase steady over longer paths. Sunlight is powerful and bright but has modest coherence. A carefully designed laser can maintain order across distances that dwarf a room. Stimulated emission is the engine of that order. An atom or molecule in an excited state can be prodded by a photon whose energy matches the gap between levels. When that happens, the emitter releases a duplicate photon, same energy, same direction, same phase. Place the gain material between mirrors so that only certain standing waves fit cleanly between them, and those waves feed themselves while others die away. The cavity defines which frequencies survive by admitting fields that add in phase after each round trip. Losses and gain balance at a threshold, and above it, a narrow, coherent beam emerges. The cavity layout and gain medium decide what kind of beam that is. Gases offer purity and high-quality modes at specific lines. Solid-state crystals store energy efficiently and can be pumped by diodes for compact devices. Semiconductor junctions fold gain, and guiding into a chip that fits on a fingertip. Add external cavities and gratings, and their lines narrow to suit precision tasks. Optical fibers doped with rare earth ions confine light tightly over long paths, combining excellent heat removal with good beam quality. Each family trades strengths, wavelength range, efficiency, pulse capability, and output power. Temporal coherence ties directly to spectral width by a simple inverse relationship. Narrow the line, lengthen the coherence, broaden the spectrum, shorten it. Mode-locked lasers take a different route to precision by phase-locking many cavity modes. The resulting train of pulses is extremely short, yet the phase relation among modes remains strict. In the frequency domain, this appears as a comb, equally spaced, sharp teeth across a broad span. Count those teeth against a microwave reference, and optical frequencies become numbers you can measure with extraordinary accuracy. The comb bridges the worlds, allowing optical clocks to define seconds with stabilities that make celestial mechanics look noisy by comparison. Spatial coherence allows tight focusing and clean interference. A beam with high spatial coherence stays narrow over long distances and can produce fringes with a single slit, many times the wavelength wide. This same property also produces speckle when the beam scatters from a rough surface. The scattered waves keep fixed relations long enough for the eye or a camera to see granular brightness. In metrology, speckle is useful. Its motion tracks vibration, its blurring tracks flow. In projection and displays, speckle is undesirable. Designers reduce it by scrambling phase with moving diffusers, by mixing modes, or by adding a small, controlled spectral width, so randomization defeats the grain without losing too much focus. Safety with coherent sources starts with understanding how the eye focuses. A small, bright beam entering the pupil concentrates power on a tiny retinal spot. Even modest outputs can harm if exposure times and wavelengths align with the eye's highest transmission. Standards assign classes to devices and specify eyewear that attenuates in the correct bands. Enclosures, interlocks, and beam dumps keep stray reflections from causing surprises, because polished metal at the wrong angle can return a tight beam without looking dramatic. Materials respond differently depending on color and pulse length. Infrared couples to vibrational modes and can heat gently through depth in some polymers. Ultraviolet breaks specific bonds and ablates with minimal thermal spread when fluence and duration are tuned correctly, a property used in microfabrication and corneal reshaping. Picosecond and femtosecond pulses deposit energy faster than heat can flow, producing precise modification before surrounding material knows what happened. In metals, pulses create melt pools, narrow and deep. In dielectrics, pulses induce localized changes in index that draw three-dimensional waveguides within glass. Metrology leans on coherence to compare phases with exquisite sensitivity. Heterodyne interferometers shift one beam's frequency slightly and measure the beat signal after recombination, converting phase drift into a radio frequency change that electronics can track in real time. Stabilized cavities provide references with line widths tiny enough that thermal expansion of the spacer and acoustic noise become visible in the data. Environmental control matters. Quiet tables, enclosed air paths, and materials with low expansion turn a simple interferometer into a recorder of nanometer scale motion that can run all day without wandering away from truth. Communications lean on coherence to pack information densely. Coherent receivers mix the incoming signal with a local oscillator and recover both amplitude and phase, allowing multi-level formats that carry more bits per symbol at lower powers. The approach demands lasers with narrow line widths and stable phase noise, dispersion maps that keep phase relations intact across long spans, and digital signal processing that compensates residual distortions. The reward is reach and capacity far beyond what intensity-only links can manage over the same fiber. Sensing at a distance benefits as well. Coherent Doppler LiDAR mixes returned light with a reference to detect tiny frequency shifts caused by motion along the line of sight. Wind fields emerge from those shifts with high temporal and spatial resolution. Frequency-modulated continuous wave systems sweep the transmitter smoothly across a band and read beat frequencies from targets. Range and velocity separate cleanly in the electrical spectrum. Because these methods measure phase and frequency rather than raw arrival times, they remain accurate in bright backgrounds that would blind simple pulse timers. Coherence is delicate, so systems often devote significant effort to preserving it. Air currents across a beam path add random phase by changing density and index. Temperature drifts alter cavity lengths and shift frequencies. Mechanical vibration shakes mirrors and modulates phase unintentionally. Solutions are practical. Shorten paths, enclose beams, actively control temperature, and apply feedback to hold frequencies against high-Q references. The physics promises precision. Engineering keeps the promise by keeping disturbances small and slow compared with the system's ability to correct them. A single line of imagery can stand beside these facts without getting in the way. Coherence is a calm cadence that instruments can follow without losing step. Then the narrative returns to the work at hand. A gain medium provides excited states. A cavity selects which phases survive. Pump power crosses a threshold, and the output stabilizes into a narrow band or a train of pulses. Mirrors with specific reflectivities set output coupling. Nonlinear crystals convert colors by sum or difference when phase matching conditions are met, yielding wavelengths the gain medium alone cannot supply. Fibers guide light, while also amplifying it when doped, combining transport and gain with manageable heat. In laboratories and factories, repeatability is the emotional anchor. A laser tuned yesterday will behave the same tomorrow within known limits if the references hold. A measurement that resolved a micron today will resolve a micron after lunch if the phase meter stays locked. Coherence brings that comfort because it replaces averages over many random emitters with a field that remembers its own timing. Even when the task is difficult, etching lines in brittle films, aligning lithography stages across a long throw, reading displacement, while platforms hum coherent light, gives the same answer when asked the same question. Nothing in this steadiness demands hurry. It rewards patient alignment and small corrections. A cavity lengthened by a fraction of a hair, a grating nudged by half a mark, a quiet current trimmed by a breath, each minute change brings the system into a narrow corridor where it will run and run. That corridor is the point of coherence. It is not flash, it is endurance. It allows clocks to test whether constants drift across seasons. It allows networks to carry symbols that would blur under less disciplined carriers. It allows surgeons to put energy where tissue will accept it and spare what lies just beside. If you need a final image before sleep, let it be brief and new. Think of a metronome heard through a wall, steady enough that you can tap along without seeing the pendulum. That is coherence, an unseen rhythm you can trust. And with that rhythm close by, the mind eases. Instruments keep their measure, beams keep their phase. When morning returns, the cavity will still resonate. The comb will still tick its teeth across the spectrum, and the same quiet cadence will be there to count on, precise as ever, kinder than it looked. Messages can ride on light without ever touching what they pass through. A slender core of glass guides the field by keeping it inside through gentle reflection at the boundary, and that guidance holds even when the strand bends along the seafloor or between city blocks. Information is placed onto that guided field by changing its intensity, its phase, its instantaneous frequency, or the orientation of its electric vector. Each choice sets how much can be carried, how far it can travel before corrections are needed, and how well it resists noise picked up along the way. The path is quiet, but the conversation is rich. Signals spread as they go because different spectral components move at slightly different effective speeds in the material. That spread, called dispersion, turns short pulses into longer ones and lets neighboring bits overlap. Engineers reduce the effect by choosing wavelengths where the glass's properties make the spread slow, by shaping the fiber so material and waveguide dispersions offset, and by asking digital processors to undo predictable distortion at the receiver. The correction depends on knowing the channel's response. Modems learn it and take it out, pushing the bits back into their intended slots so they can be read without guessing. Many separate channels can share one filament by assigning each a distinct color. This wavelength division approach turns a single core into a bundle of parallel paths that do not mix because the device at each end keeps their colors apart. In long links, amplifiers inside the glass itself lift all those colors at once. A short section doped with rare earth ions gains energy from a pump and hands that energy to the signals without turning them into electricity and back again. The approach keeps noise low and efficiency high over great distances, which is why repeaters buried in the ocean can run for years with only small inputs of power from conductors woven into the cable jacket. Traffic does not always need to flow end to end. Network elements can add or remove selected colors while letting the rest pass undisturbed, allowing routes to change as demand changes without tearing the system apart. These add-drop functions work because filters can be made narrow and stable, responding strongly to one band while ignoring its neighbors. The result is a fabric that can be rearranged in place, keeping busy paths close to their capacities, while still leaving room for new work to join where it should. Above ground, beams can carry data through air. Free space links trade the protection of glass for the convenience of not laying cable. Their narrow divergence and high carrier frequency offer capacity and privacy, but they answer to air's changes. Heat ripples and wind shear break a clean beam into dancing patches at the receiver. Systems answer with adaptive optics, that reshape the inbound wavefront in real time, and with coding that spreads symbols across time and space, so that a few bad moments do not erase meaning. Between satellites, vacuum removes the turbulence and leaves only pointing as the main difficulty. Fine attitude control and tracking solve it, and once solved, the path is stable and fast. Timing is a quieter variant of the same idea. Instead of carrying arbitrary data, a link can carry a disciplined rhythm. A stabilized laser and a frequency comb define evenly spaced markers across a wide band. Those markers can be carried through fiber, so that a clock at the far end counts the same seconds as the source. If the path length changes with temperature or strain, the round-trip phase reveals the change and allows the sender to pre-compensate, keeping the ticks aligned. With that alignment, radio telescopes far apart can combine their recordings as if they were facets of a single large dish. The sky becomes sharper because the timing is sure. Cities carry a different need. Many very short runs that must move data in and out of processors without boiling the room. Short fibers and integrated waveguides bring modulators and detectors close to the chips that compute. The goal here is not only rate, but also efficiency, how many joules per bit the system spends to move information a short distance. Designs that encode multiple levels in one symbol, and that recover both amplitude and phase with coherent receivers, lift capacity without growing the optical power dangerously high. The trade is complexity in signal processing, which modern hardware accepts in exchange for quieter thermal loads. Security can ride on light in a way that ordinary interception cannot imitate without leaving a trace. Key distribution that relies on quantum states sends individual quanta or correlated pairs across a path and checks statistics that would change if an eavesdropper measured them. The result is not a channel immune to disturbance, but a way to learn whether disturbance occurred. It complements classical encryption by creating keys with evidence of integrity. The practicalities, matter losses, detector imperfections, and background and systems include checks that account for them. When the numbers agree with expectations, the key is accepted. When they do not, it is rejected and tried again. Sensing uses the same strands, not as highways, but as instruments. A long fiber reflects tiny fractions of light from imperfections all along its length. If the source and receiver listen to those faint returns carefully, they can read changes in phase that reveal motion and strain at many points at once. A buried cable becomes an array that hears footsteps, vehicle passes, and landslides as minute stretches shift the backscattered field. The method depends on coherence and on algorithms that turn small phase changes into locations and magnitudes without adding hardware along the route. It is a simple use of something that is already there. Distance and shape come back from light by timing. A pulse leaves, scatters or reflects, and returns. Its time of flight becomes range. Sweep the beam across angles, and a map appears. A different scheme sweeps the frequency smoothly and reads the beat between the outbound and inbound fields at the receiver. That beat encodes range and motion in separate terms that electronics can separate. The method works in full sun because it reads frequency rather than brightness alone, and it allows high precision with modest power because the measurement is differential rather than absolute. Underwater, the same principles apply within limits set by absorption and scatter. Short blue-green bands reach far enough to carry modest links between vehicles or nodes. Careful pointing and coding carry messages in coastal waters where radio cannot help and sound is slow. In clean air across a campus quad, an infrared beam can connect two buildings quickly while trenching is planned. In either case, the link is fast but sensitive to fog, rain, or spray. Monitoring and fallbacks keep service from failing when the path dims. Routes on land and sea require enduring hardware. Repeaters on the ocean floor share pressure housings with power feed, equipment, and branching units that direct flows toward multiple shores. The design priority is low touch. A device should run for years without asking for help. Failures are rare, but planned for with protection paths and spare spectrum that can be lit to fill gaps while repairs proceed. On land, conduits follow rights of way and bundle many fibers to allow growth without fresh construction. The core technology inside the glass barely changes from shore to rack. The variety lies in how it is managed and protected. As rates rise, the field borrows tricks from radio. Polarization becomes a place to put symbols. Orthogonal states carry separate streams that receivers sort out with digital filters. Phase modulation formats let each symbol encode more than a single bit, trading distance for capacity in controlled ways. Forward error correction spends a small overhead to catch and repair mistakes caused by noise and distortions. The cost is complexity in encoding and decoding. The gain is a clean stream at the far end, even when the path is long and the power per channel is modest. The air around the beam still matters in short runs. Temperature gradients bend paths and change delays. Cables expand and contract with weather. Connectors age and build small reflections that leave faint ghost copies of old symbols behind new ones. System designs budget for these imperfections. Maintenance practices keep connectors clean and bend radii gentle. Monitoring looks for error rates rising and corrects before users notice. The network's steadiness is not an accident. It is a series of small caretaking acts, guided by numbers that tell when each is due. A single line of imagery can sit here briefly and then make room again. Imagine a lattice of clear roads where traffic flows in many layers without horns or crossings. That is enough. The facts hold the comfort. Glass confines by design. Colors share space without crosstalk. Amplifiers lift every lane at once. Filters pick one lane gently out of many. Lasers hold phase, so receivers can read symbols that lie in angle and orientation as well as height. Codes repair small wounds. Clocks ride along and keep their beat on the far shore. In this web, connection feels less like noise and more like breath. The same physical rules that send a spectrum across a prism carry a thought across an ocean. The mechanisms are consistent whether the span is a room or a continent. They do not need hurry to work. They need alignment and patience. That is why the system stays calm even under great load. It is not improvising in a storm. It is following rules that were quiet long before the cables were laid. As night deepens, that dependability is a kind companion. If a page loads, it is because a filament of glass obeyed internal reflection 1 billion times without failing once. If clocks at two ends agree, it is because a phase held still across changes that could have jostled it. The network's light does not glare. It moves inside, guided, measured, and corrected. When morning comes, the strands will still carry their many colors side by side. The same roots will still be there, ready without complaint, as if the planet had grown threads that know only how to keep a rhythm steady. Turning light into a measurement means turning an unknown into something that a field can reveal. A beam spread into its component colors will show narrow dips or peaks where atoms and molecules interact strongly. Those features identify the species present, and their depths and widths say how much is there and under what conditions. If a gas sits in the path, its characteristic bands carve gaps in the spectrum. If a flame or discharge sits there instead, sharp lines brighten at the energies it prefers to emit. A different conversation occurs when light loses or gains a small amount of energy by shaking bonds in matter. That inelastic shift produces a fingerprint that maps vibrations and can tell similar chemicals apart, even in mixtures. These approaches see beyond transparency. A clear liquid looks empty to the eye, but carries telltale structures that appear when a spectrometer listens to small changes in color or tiny shifts around a line. Solids with similar appearance under white light separate cleanly when their vibrational bands are compared. The measurement does not push or pull. It registers how a field and a structure exchange energy in precise steps that do not depend on guesswork. Results come in wavelengths and intensities that trace back to constants rather than to ad hoc scales. Looking small has long been limited by the fact that waves spread. Finer detail needs shorter wavelengths or wider lenses, and living cells do not welcome high-energy beams or long exposures. A path around the barrier appears when emitters can be switched in small groups or forced to turn off at the edges of a focused spot. In one method, a bright ring cancels fluorescence in a donut around a central point, leaving only a tiny region to shine. Scanning that region across a sample writes detail finer than a classical focus would allow. Another method keeps most fluorescent tags dark, while a random, sparse subset turns on. Their centers are found precisely by fitting, and many such frames build a map with points placed far closer together than the old rules would tolerate. The common idea is not to break physics, but to ask narrower questions in each instant, so the answers can be placed where they truly belong. Tissue is layered and scattering. Light sent in returns from many depths at once, unless timing can separate echoes. A source with a short coherence length sends a field whose self-agreement fades over small path differences. Interference appears only when the return matches the reference closely in distance, so scanning the reference length selects depth. Cross-sections arise. Without cutting, showing bands and boundaries in living structures that would be dangerous to touch. The method shines in the eye because the retina tolerates careful light and because the layer structure is informative for health. It also sees plaques in vessels and patterns in skin where conventional imaging struggles. Surgeons use light to guide hands when appearances mislead. A marker that binds to a target tissue and glows under a specific color can outline margins that look normal otherwise. The glow is not paint, it is an emission from a molecule designed to respond in a band where backgrounds are small and tissue transmits well. The surgeon follows a live map that only illumination can reveal. In other treatments, a drug lies dormant until a chosen color wakes it. The light activates chemistry that damages nearby cells and then fades as soon as the source is removed. Beam path and placement become dosage. Regions spared by shadow or distance do not feel the effect. Physiology reports itself through absorption changes that repeat with each heartbeat. Blood in arteries brightens and dims a thin path through tissue as pressure rises and falls. Sensors at the skin record that tiny modulation at two colors that oxygenated and deoxygenated hemoglobin absorb differently. By comparing the changing parts of those signals, the device estimates how saturated the blood is with oxygen. Motion and ambient light can confuse the reading, so algorithms watch for patterns that are unphysical and set limits on how quickly a real value should drift, turning a simple optical ratio into a trusted vital sign. Brain activity rearranges blood flow and oxygenation over seconds. Light in the near-infrared reaches a short distance into tissue and returns carrying information about those changes. With careful placement and subtraction to remove shallow layers, patterns emerge that show how regions respond during tasks. The method is not as sharp as magnetic or electrical recordings, but it is quiet, safe, and portable, and it reads a physiology that complements what other tools see. In small patients or bedside monitoring, Light-based approaches can reveal trends that guide care without moving a person into a large machine. Breath holds markers of metabolism at trace levels. Lasers tuned to narrow absorption features can read those markers along a short path without concentrating the sample. The instrument scans a small region around each line and compares what comes through with a clean reference. The difference reveals how much of the gas is present. Because lines sit at precise, known places, the method can separate overlapping species and tolerate modest changes in pressure and temperature if it accounts for how those change line shapes. The same approach checks leaks of industrial gases in open air, measuring safety and compliance without bottles or pumps. Distance becomes length in optical terms by counting cycles rather than stretching tapes. A beam with a stable frequency defines a wavelength in free space. If a device can compare path lengths to a fraction of that wavelength by interference, it can measure displacements and rotations with very small uncertainty. Factories use such systems to align components where micrometers matter. Builders of instruments use them to set mirror positions inside machines that need to remain quiet against drift. In national labs, stabilized lasers anchored to atomic transitions define units by constants rather than by artifacts, so that a meter means the same thing in every place and season. Safety sits beside precision. Illumination levels must keep tissue within comfortable limits. Wavelengths must avoid those bands where the eye focuses strongly onto delicate structures. Exposures must be brief enough that heat never accumulates to harm. Standards guide these choices with margins that assume worst reasonable cases. Devices include shutters that fall closed if power rises unexpectedly or if alignment drifts toward a region that should not be lit. The same care appears in factories, where enclosures and grounded mounts keep bright beams from reaching people, and where windows block the specific band used inside. Light helps when contact is difficult or unwise. A surface can be mapped by projecting a known pattern and recording how it distorts. A moving part can be monitored by measuring how its reflected field's phase shifts over time. A fluid's motion can be read by tracking how scattered light picks up a tiny frequency shift when particles ride the flow. Each method converts a mechanical or chemical detail into a change in a field that instruments know how to count or compare. The conversion is clean because it leaves the subject largely untouched. Numbers become trustworthy not only when devices are careful, but when the chain from raw data to result is transparent. Calibration with known references, checks against independent methods, and honest statements of uncertainty knit confidence into the measurement. Optical tools invite this discipline because their steps are modular and stable. A wavelength is linked to a frequency, a time to a path, a line depth to a concentration. When tools disagree, the disagreement can be traced along that chain to find where assumptions parted ways. A single small image can rest here, then leave space again. Light is a gentle fingertip that can feel a pulse without pressing. The anchor is not the image, though. It is the repeatability that follows careful use. Spectra identify compounds because the same transitions appear every time. Cross-sections in tissue align with anatomy because interference selects depth reliably. Distance meters reach the same answer at noon and at dusk because the reference is intrinsic to the field, not to a piece of metal warmed by the room. As the day quiets, there is ease in knowing that these methods will greet the morning unchanged. A patch of skin will show its layers when asked, with the proper band. A sample will show its composition when spread into colors. A device will report a length the same way it did yesterday, counted in cycles against a timekeeper that does not wander. This is not showiness. It is patience organized into tools. The light you do not notice in a clinic hallway or on a lab bench contains that patience. It makes the invisible visible without demanding attention beyond a calm look. When rest comes, the instruments keep their quiet promises. They do not argue with the subject or with each other. They ask narrow questions and receive clear answers. In the morning, they will ask again and receive the same. In that steadiness lies the reason we trust them to guide hands in surgery, reveal changes in a cell, and define how far apart 2 points are in a shop or in space. Light remains at a small distance from what it measures, and yet it understands it intimately. That distance is a kindness. It lets knowledge arrive without harm, and it lets sleep arrive without worry. Across all of this, light is steady without being simple. It travels without a carrier, yet it carries so much. It acts like a wave when we ask about phases and interference. It acts like a quantum when we ask how energy moves from one place to another. It colors the world because sources differ and surfaces choose, and because our eyes compare rather than measure absolutely. It bends at boundaries, spreads around edges, and writes maps from patterns that emerge when paths align. Instruments built from these same rules gather detail from the near and the far, turn glow into temperature, and turn timing into distance. You do not need to hold every rule at once. It is enough to remember that fields sustain fields, that color is frequency, that structure guides and splits, that light's touch can push, heal, and reveal without incision. In buildings and cables, in skies and seas, the same equations whisper the same outcomes with patient consistency. When you see a surface soften under a cloud, when a screen brightens with a click, when a sensor notices a pulse at your wrist, you are watching the same traveler perform different tasks in familiar rooms. If you want a brief picture to keep, choose a quiet one. Imagine a line that never droops, crossed by crests that pass and pass, leaving no dust behind, yet shifting everything they meet in measured amounts. That line is not a path drawn by chalk. It is relation between electric and magnetic, between source and sensor, between star and eye. Where matter offers structure, light takes the offer and shows the shape. Where matter offers energy, light takes the step and carries it forward. Let your breathing match a slow cadence. Facts can rest while they settle into memory. Polarization is orientation. Interference is addition and subtraction. Dispersion is color arranged by timing. Scattering is preference written by size. Networks glow invisibly beneath streets and seas. Clocks agree across mountains. And instruments watch the small while respecting what they watch. These are not separate stories. They are one continuous thread tying measurement to meaning. If sleep is near, let it arrive while the traveler keeps moving. Somewhere, a signal threads an ocean of glass. Somewhere else, a faint spectrum from a distant cloud finds a mirror cooled against its own warmth. Light goes on without fatigue. We use it because it is faithful, and we listen because it says exactly what conditions allow. Let that steadiness soften the room. Let the regular pulse of waves and the patience of photons set your breath. Everyone who's made it this far, leave us a soft little signal in the comments. Just say, "I'm here," share this moment, and subscribe so our next night walk finds you easily. Close your eyes now. The path is marked by small lamps you can visit again when you wake. Good night.